So in this video we're going to talk a little bit about Newtonian gravity. We talked a little bit about gravitation, or the force that the Earth exerts on objects near its surface, a couple of videos ago. And in that video what we talked about was to say that the force that the Earth exerts on an object is equal to the mass of the object times the local gravitational acceleration, where g is roughly 9.8 meters per second square. Now it turns out that this is an approximate form to the actual interaction between objects that have mass. So I want to ground this for a moment for you and suggest that we have the Earth and the Moon, and as I'm sure you already know, their interaction is gravitational. The reason that the Moon revolves around the Earth is because of this gravitational interaction between the Earth and the Moon. You know that it's also attractive, I'm sure. That is, that the force that the Moon exerts on the Earth is towards the Moon, and the force that the Moon exerts, that the Earth exerts on the Moon is towards the Earth. So they act along this line between the two. Now, the more general description of gravitation, or the gravitational force, comes from Newton, who hypothesized this model that the gravitational interaction between two objects is equal to minus a constant, this capital G, which we'll talk about in a minute, times the mass of the two objects divided by their separation squared times the unit vector that points from one to the other. So you have to be really explicit here because the direction is attractive, so this r vector is defined depending on which of these forces you're looking at. The constant g is 6.67 times 10 to the minus 11 Newton meters square per kilogram square. And it's a fundamental constant of nature. It describes exactly how strong this interaction is between these two objects. So all objects experience this force. The force between me and this chalkboard is very, very small. It comes from these astronomical objects, or these planetary bodies, where these forces actually matter. And that's why the interaction that you are mainly concerned with on the Earth is due to the Earth and not due to objects that are interacting with other objects due to their mass. So let's tease out this equation just a moment. So we're going to write down the force that the Moon exerts on the Earth. We're going to be very explicit here. So that's minus g times the mass of the Earth times the mass of the Moon divided by a vector that points from the Moon to the Earth. So if we're going to draw this picture again, here's the Earth, here's the Moon. The vector that we're talking about is that vector. That's our Moon, Earth. And the force that we're talking about is that one. So you can see why we need this minus sign, because the vector points from the Moon to the Earth, but the force actually points towards the Moon. Now, what's really curious here is that if we were to calculate the force that the Earth exerts on the Moon, this would look almost exactly the same. There'd be a minus g, mass of the Earth, mass of the Moon. But now our vectors are just slightly different, because what they do is it locates the Earth, or the Moon, with respect to the Earth. So the vector that is our Earth-Moon points in this direction, and the force points opposite that direction. Oops, Earth-Moon. So you can see that these two forces have the same magnitude, they're the same size, they point in opposite directions. This is actually our first example of a Newton's third law pair. Newton's third law stems from the idea that a force is an interaction between two objects. And so these two objects exert forces on each other of the same size but in opposite directions. This is very different from a video ago when we talked about this fan cart having an interaction due to the Earth and an interaction due to the track. There are three objects in this system: the track, the Earth, and the cart itself. These two forces, while they are the same size and in opposite directions, are not Newton's third law pairs. These forces, which are due and acting on the two objects in the system are Newton's third law pairs. The final thing I want to just mention briefly is how do we deal with this sort of mg business, right? Near the surface of the Earth, what is it that matters? So I'm going to calculate the magnitude of the force that acts on an object near the surface of the Earth. So if we're talking about the surface of the Earth, what we're going to do is we're going to have somebody standing a distance r Earth away right here, and they have a mass little m. So if we go to calculate the magnitude of that force, what we're going to find is it's equal to g, mass of the Earth, mass of the person, divided by the radius of the Earth squared. But that has to be equal to little m times g, which is the gravitational acceleration near the surface of the Earth. These two m's are the same m, so what we have here is actually a definition for the gravitational acceleration in terms of fundamental constants. The big G, the mass of the Earth, and the radius of the Earth squared. So this is how we resolve this issue of the gravitational interaction is actually an interaction where the position actually matters. When we're near the surface of the Earth, the radius of the Earth is fixed, the mass of the Earth is fixed, and so this is a constant value over the surface of the Earth. Now, you might wonder, well, what are we going to use this for? We might actually start predicting motion with it because we have this idea of the iterative prediction process. We can calculate the force in small time steps. So we can actually model the motion of, say, a comet around a planet using iterative prediction of motion. So you might do that at some point later.